In this class, we're going to look at yet another application of integrals. But this is the first time, although it will not be the last, in which the application is to something other than a geometrical object. In fact, we're going to look at a physics application of integrals, and in a way, this is going to be one of the most interesting ones, because it's one where the integral comes out of presumably nowhere, in the sense that we may not expect to be able to use integrals in this situation. But integrals do occur, and so we're going to see how, and I'm going to give a couple of examples of how this process works, and then in class we're going to see some more, and hopefully you're going to discover and explore some more on your own. So first of all, what do we mean by work? No, it's not this fella here who is sitting at his desk like I do most of my days, punching away at computers or calculators or whatever, just completing a task. We're going to be looking at a different concept of work. Well, what about people actually working in a very physical sense? Well, we're getting close to it, but not even that. And no, we're not talking about Superwoman shoveling your driveway or all the work that we do when we're trying to exercise or running off all our extra pounds. No, the idea of work that we are going to be analyzing, although I have to say integrals will probably be useful in any one of the situations depicted here, but the situation we're going to be looking at is a very abstract physics situation. So what we're going to be looking at is a situation where you have a force which is applied to an object, and I'm sure you have seen this in other contexts, in other courses. So here we have an object, and here is someone who is trying to apply a force to this object. Okay, so the force is often represented as an arrow. Echoes of linear algebra in a way, but this is not everything that we need in order to do work. Now, if in fact this truck stays there and goes nowhere, and this guy keeps pushing and pushing and pushing, the guy may end up being exhausted, but still hasn't done any work as far as physicists are concerned. Because in order to have work in the physics context, what we need is some movement. So this force must move the object by a certain distance d. If all this happens, so we have a force pushing an object and pushing it by a distance of d, then by definition the work done by the force is going to be equal to the product of the force applied times the distance that it has moved. And this is what we're going to be looking at. Now you might say, where do integrals come in all this? This is a very simple formula, it implies just a product. True, but this simple equation only applies under a very basic assumption, namely that the force is going to be constant. Well, what if that is not true? What does that mean? Well, it can mean one of several things, but I'm just going to point out the two most common ones that we're going to see here. Namely, one situation may be that the force is not going to be constant throughout the action. And therefore, we cannot simply multiply F by D because F is not a number, but is going to be some varying quantity, varying with time or position or whatnot. The other situation in which the constancy assumption is not true anymore is if not all parts of the object are moved by the same amount. Maybe some pieces are moved more, some pieces are moved less. And so in this situation again, what amount of distance are we going to use? The one of one piece or the one of the other? Well, we have to use all of those. So how are we going to do it? Well, we're going to use the slice, approximate, add up, take the limit method, and we're going to be able to see what happens when either the force is not constant or not all pieces get moved by the same amount. Let me give a couple of examples. One classical example of this idea of computing work is when we consider the work done to stretch or compress a spring. I'm going to just show you the situation for the stretching. The compression works exactly the same way. Now, first of all, what are we talking about? Well, let's say we have a spring which in its relaxed neutral state has some length, which we're going to assume to be 0, but doesn't have to be. But we're just going to say, well, this level here, the position that the spring has at this point, that's your position 0. That's the initial position, the rest position. Alright, what we may want to do is actually, let's say that for whatever reason, the spring has actually become a little bit longer, so is in position S1. And what we're going to do is we're going to apply a force to this spring. Okay? And this force is going to stretch the spring up to a different amount, S2. Now what we want to know is, well, how much work has been done on the spring so as to move it from position S1 to position S2? Well, in order to be able to compute this, we need to know something about springs. And what we're going to be using is the famous Hooke's law, which says that when you do this kind of process, then the force that you need to apply to the spring is proportional to the distance from equilibrium position. And this is something that I'm sure you have seen, you have experienced personally. If you're trying to stretch a spring, at the beginning it's very easy to do. All you need to do is apply very little force, but then as the spring stretches more and more, you have to apply more and more force. And that's what the Hooke's law is saying. So this is one situation where the force actually is varying. It changes according to the position, according to where we're at. So in order to compute the work done by this force, we cannot simply multiply F because F is changing. So what are we going to do? Well, we're going to use our good old method. So first of all, we're going to slice. So what that means is that we're going to think of this whole process of moving the spring from position S1 to position S2. We're going to break it down into a whole bunch of small little movements from one position to a position nearby. So let's say we start from the spring in this position and we stretch it up to just a little bit more. Okay. So, well, how much more? Well, let's say that the distance that we've moved is, with the usual notation, delta S. So it's just a little amount of S. So what we're going to do at this point is we're going to approximate. So what does that mean? That means that we're going to assume that within that tiny little fraction of a movement, the force is actually going to be constant. So in other words, we can assume that the force being applied to the spring is going to be equal to K, which, by the way, is the constant associated to the spring. We're going to assume that that doesn't change. It'll be an interesting thing to see what happens when K itself changes. I'll leave that to you as an exercise, as a further exploration. But for now, let's say that, again, within this little distance delta S, the force is not changing because S is practically constant. Not quite, but that's what we're approximating. And so what we're going to do is we're going to say, all right, the amount of work which is being done to stretch that little bit is going to be equal to F times delta S. And in this case, the approximation is that it's going to be equal to Ks times delta S. The force is K times the distance, and then we're going to multiply that by how much we have stretched the spring. Now I'm noticing right now that I have some capital S's and some lowercase s's. Just ignore that and pretend that they're both the same. Don't worry about this little detail. Alright, so that's the approximation, and now what we have to do is we have to add up all the little works that are done to stretch the spring more and more and more. When we do that, we're going to end up with the work being equal to, well, okay, what do we have? For each of the little stretches, the work is going to be equal to Ks times delta S. So what we have to do is we have to add up all of these. And then, of course, in order to get an exact value, we have to take the limit as n goes to infinity of all those stretches. Remember, those little amounts of work that we computed were approximate. They're going to be equal only in the limit. But notice what we've done. We've just constructed an integral, right? It's not any different from the situation where we're looking at areas or volumes. It's just applied in a different situation. The formula still looks like the limit as n goes to infinity of the sum from 1 to n of some function of the variable, which in our case is s, times the differential of the variable, which is delta s. And therefore, that is going to be equal simply to the integral from a to b, where a and b are going to be the initial and final position of the spring. So in the case that you have up here, will be s1 and s2 of ks ds. As you can see, this is a very simple integral. K is a constant, can even come out of the integral. The antiderivative of s is quite clearly s squared over 2. So the calculations from now on are going to be very easy. Now let's look at something a little bit more complicated. How about rocket science?